bit easier than you might anticipate. What does our answer need to be? Moles of oxygen. What is our symbol for oxygen? O2. Why do we know it's O2 and not O? It's a diatomic molecule and it does not specifically say oxygen atoms. If it says oxygen atoms, then it's just one oxygen. Okay? Since it just says oxygen, we are assumed in the elemental state, we are assumed diatomic. Okay? Right or wrong, that's just what we have to assume. What were we given? 2.25 moles of nitrogen, and our symbol for nitrogen? N2. Okay? Are moles of nitrogen the same thing as moles of oxygen? No. So I have to do a conversion. Okay? And this is where things get dicey here, where I'm noticing people going off and doing different conversions. Okay? We talked about Avogadro's number. Can I use Avogadro's number to convert the moles of nitrogen to something? Yes. Yeah, I could. Whoops. That's why we write our units first. Moles of nitrogen to Avogadro's number would allow me to convert it to, and not grams, atoms or molecules of nitrogen. Okay? Or we can be super generic and say particles. That way we don't have to be confused of atoms or molecules. We can just say particle. It's the same thing. Okay? 1 mole is 6.022 times 10 to the 23rd particles. What unit would I now have? Would I have particles of nitrogen? Well, is that what I want as an answer? No. Okay. Well, I could convert 6.022 times 10 to the 23rd particles. I could convert it into moles by doing what? Reversing the calculation I just did. Okay, so maybe we weren't supposed to do that. What? I said maybe we weren't supposed to do that. What do we want to convert moles of nitrogen to? Moles of oxygen. So instead of just guessing and throwing something in there, I guess I'll announce next time, don't write this down. Sorry. We want moles of oxygen. So before you just start blindly converting, ask yourself, do I have a conversion factor that allows me to convert between those? Simon, you're saying yes. Where do you get that conversion factor? Okay, from the equation. Remember when the question first popped up, there was no equation. And Chandler said, that doesn't work. I need an equation to figure out the relationship between two different substances. Okay? So we'll use the equation. What does the equation need to be? Balanced. Is the equation balanced? No, I real quickly erased. Okay? And as Sebastian pointed out to me correctly, because I wasn't paying attention, okay, is balancing it going to have an effect on this solve? No, because we're looking for the coefficients in front of what? Oxygen and nitrogen. When we balance the equation, do those coefficients change? No. So in this case, we could get lucky and not balance it. Okay? Luck is not a good thing for an exam. Please don't get lucky. Okay? Please get it right. Okay? And for the right reasons. What is the number that needs to show up in front of moles of O2? 1. What is the number that needs to show up in front of moles of N2? 1. What's my answer? 2.25 moles of O2. That's it. That's the answer. Your units set up the work. Follow your units out. What if I had changed the question and instead of asking for the moles of oxygen to react, I want the moles of nitrogen, eraser, of nitrogen oxide produced. How does that change everything?
Well, first off, we're not going to be finding moles of O2.
I'm not trying to find moles of O2, so let's fix that. What do I need to find?
nitroxide.
Moles of nitrogen monoxide. Okay. How do I change my calculation? Are moles of nitrogen the same as moles of nitrogen oxide? No, so what do I need to do?
Conversion factor.
Conversion factor. Ideally, the conversion factor, the unit that shows up in the bottom of my conversion factor is? I want it to cancel. What am I canceling it with? The moles of the nitrogen. What unit do I want to have show up on top? Moles of nitrogen monoxide. Why did I pick nitrogen monoxide to be on top?
That's the one you want.
That's what I want for my answer. What numbers show up in front of those conversion factors? 2 and 1. Where does the 2 show up?
On the equation.
In the equation. Where in the equation? Where does the 2 show up?
To the left of the...
So I see a 2 there, yeah? Where does that 2 need to go into my conversion factor?
On top.
I've been fishing for on top, and you know I'm going to yell at you for that. No. Denominator's bad too. Numerator's bad too. Where does it go? In front of moles of nitrogen monoxide. Okay? Okay, we have to be very specific in how we answer that question. Okay, if we start saying on top, then what are you going to do? Every time you have a number, you're going to put it on top. No, the number goes with the unit. Okay? Because there's a 2 in front of the nitrogen monoxide in our balanced equation, the 2 needs to show up in front of nitrogen monoxide in our conversion factor. Okay? Which could be on top, it could also be on the bottom. So be very careful in your referencing. What shows up in front of moles of nitrogen? 1, our coefficient from our equation. What happens? Our units cancel, and we'd have 4.5 moles of nitrogen monoxide. We've now done our conversion factor. Kind of makes sense?
It does. It looks easy, but I know when it comes down to like solving for it.
Okay.
Just like,
So,
do it again.
let's address a couple things about ease. As it's written, it looks really easy. Why? This is the answer. Okay? When you look at an answer, it's really easy. Okay? When does it become difficult?
When you have to find
Putting
the
in the plate.
When there's no answer written down. Okay? This is the part that you have to work through. Okay? So when we talk about this, and if you look at your notes, how many of you wrote down the questions that I asked you? One person wrote down the questions that I asked you. How many of you wrote down all the work? Interesting. Why are you writing down the work? The work is the answer. Does that tell you how to get to the answer?
yes.
It doesn't tell you anything about how we got there. It says that's the proper way to put those things in. If you don't come up with the proper questions to place those numbers and those units in the right space, you have no context. Your notes should not be writing down the answer per se, but writing down the questions that were asked to get you there. The very first question was, what do we want? The moles of oxygen, in this case. What was the next question?
Where do we start?
What were we given? What was the next question? Are those units the same? Okay, no, which means conversion factor. What do I want for a conversion factor? Focusing again on where I'm trying to get to and what I have, and making sure that those units can somehow disappear or appear. Moles of nitrogen, moles of O2. Why did I pick those units and place them in those locations? I'm trying to get rid of one, I'm trying to get the other. Okay? It's asking the question of what do I need to do to make this equation work? Where do I get the numbers? From the coefficients of the balanced equation. Okay? Those are the questions you need to be asking. Not how many moles of oxygen are produced or needed to react. That question is the hard question. You need to ask all of the easier steps along the way. Okay? If we tie this back to our writing, okay, what is your proper format for writing? Sit down, type out a 1,000-page, that's a bit excessive for our assignments. 1,000-word document. Okay? We just tell you sit down, your 1,000-page blog is due Thursday. How many of you are going to freak out?
It's not going to be good, but it's not going to freak out.
Okay. Probably not going to be the greatest thing. What do we have you do? We do smaller bits and work our way up to it. Why? It's easier to tackle smaller bits than it is to tackle the whole assignment. Same thing is happening when we go through and solve. You need to be coming up with the process to get you there, not doing it in one giant leap. Okay? Slow it down, you'll do better. Okay? Okay, so that's all that work. So, let's make it more difficult. New problem. This is mildly more difficult because it's only a new question. Okay. And we can all yell at Michael for this because he asked for it to be more difficult. How many moles of carbon dioxide? Yeah, I guess we should be careful which Michael. You could say it was me. I'm talking about myself in the third person. How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Set up the problem, set up the work.
Because there's 2 on the right, yeah.
Okay, sounds like we're getting excited about this. Hopefully, maybe we can get this figured out. The very first question is... No. What do we want? When do we want it? We want moles of CO2. That's what the question is asking for. We have to be able to identify within the question, right? Using our reading comprehension and English skills to interpret what we want. Right? What are we given? Nothing. Sorry. 1 mole. Okay? Here's the question that I've been asking. How many of you wrote out SODIUMHYDROGENCR, whatever the rest of that, too many letters? How many of you wrote that out? Really? You wrote all that out? Oh, bravo. Did anybody else write it out? Okay. What did you write out instead? Guess what's embedded within this question?
Nomenclature.
Nomenclature. Okay. It also says sodium carbonate at the very beginning. So it doesn't give you the formula. There are similar formulas within that, depending on which one. If you don't know your nomenclature, you wouldn't be able to match up nicely. Okay. So ideally, it is common knowledge at this point because you've been practicing your nomenclature and it's just an immediate response. It's not this slow, which one is it? Okay. Is sodium hydrogen carbonate the same thing as CO2?
No.
So what do we need?
Conversion.
Conversion factor. What do we know about our conversion factor? Or what would we hope about our conversion factor?
That's easy.
We want to get rid of moles of sodium hydrogen carbonate. That unit needs to show up on the bottom. This is my ideal world environment. What do I want to convert to? Moles of CO2. Do I have a conversion factor that allows me to convert between those two? Yes, that conversion factor is found in the chemical equation. It's the coefficients from our chemical equation. What is the coefficient in front of CO2? Well, first off, is it balanced? Yes. Okay. In theory, I balanced that nicely. What is the coefficient in front of CO2? 1. What is the coefficient in front of sodium hydrogen carbonate? 2. Where do those numbers show up in my conversion factor?
The 1 goes in front of the CO2.
The 1 goes in front of the moles of CO2. The 2 goes in front of the moles of sodium hydrogen carbonate. So we can now do our calculation. 1 times 1 is 1. 1 times 2 is 2. And I can get half a mole of CO2. If I don't want to write it as a fraction, I could write it as 0.5 moles of CO2.
The fractions are more accurate.
Not in this case. Okay? Questions about that? I'm going to throw Sebastian under the bus. He said that was too easy.
I didn't say that.
What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of carbon dioxide are consumed? We're now scaling this up. We have to incorporate more conversion factors. Okay. This one will in fact involve 2. Again, these are the 2 steps that should have already instantly, every time you solve a problem, this work needs to show up. You need to write down what you want for your units and what you start with, and then hope for the best. Okay? Ideally, we would have 1 conversion factor. I already elucidated to the fact that there are 2 conversion factors necessary to run this one. It is possible that you could use more than that if you did some different unit conversions, but you can do it most efficiently with 2. Okay? And our very first step, do we want moles of CO2 in our answer? No, so we know moles of CO2 needs to show up down below. What do we want to have show up on top? Careful, what do we want?
Grams.
We would ideally want grams of sodium hydrogen carbonate. Is that conversion factor existing? Bad. This is one of those don't write things. Yes, sorry. So wait till I finish putting numbers in. When I put numbers in, it's good. Okay? If you want to try and copy it. Thank you for reminding me. So we don't know that conversion factor. Okay, that doesn't exist. This now opens the door, because now I can convert moles of CO2 to anything I want. Okay? I could theoretically go into grams of CO2. I could go into atoms or molecules of CO2. I can go into atoms of carbon. I could go into atoms of oxygen. Okay? But what conversion factor gets me closer to where I'm trying to get to? Moles, I like that unit. Moles of what? Sodium hydrogen carbonate. Okay? Because that's what I want for my answer. That's the unit, part of the unit I'm trying for. Okay? I cannot convert substances through any other unit than moles. Kind of a lie, but that's good enough. Okay? Moles is the only way to convert substances. So if we look at our conversion and we know we need to go to a different substance, we need to use a mole-mole ratio. That mole-mole ratio is found. What?
I was just repeating you.
Okay. Our mole ratio is found where? Coefficients from our balanced equation. Okay. What number should show up in front of sodium hydrogen carbonate? 2, because there's a 2 in front of it in the equation. What number should show up in front of moles of CO2? 1. Did you start just throwing numbers in first? Okay. So what we want to do is focus on the units. The units will tell you when the numbers can go in. For those of you copying, that conversion factor is now okay. Okay. What unit would we now have? Moles of sodium hydrogen carbonate. Is that what I want for my final answer? So what do I need to do? I need to keep converting. I want to get rid of moles of sodium hydrogen carbonate, so I know it needs to show up on the bottom. What unit do I ideally want to show up on top? Grams of sodium hydrogen carbonate. Where do I find that information? That comes from the periodic table and adding up the molar masses for every single one of our elements. Right? Which I've seen a couple people's calculations, I believe comes out to 84 and change. Okay, 84.07, 08, 1. Okay, which then means we can then punch it into the calculator, because what do our units then have? Grams of sodium hydrogen carbonate. The calculator spits out 336. Is that right? 0.04 grams of sodium hydrogen carbonate, and as some people started to scream and get irritated about, we would then be wrong. What is wrong with that answer? I'll come back to your statement in just a second, Jocelyn. Sig figs, how many sig figs did we start with? Only one. How many sig figs did we write out? A lot more than one. We need to convert that so it becomes 300 grams would be our official answer. Okay. Yes, that's irritating. How is that fixed? Typically what you'd be asked is not 2 moles. You'd be asked 2.00 moles. Then we'd have 3 sig figs and everything's happy. Okay? So, Jocelyn, you said something about multiplying by 2. No. Okay. We've already factored in our mole equation into our solve. Okay? That's what our conversion factors were set up and designed to do. I noticed that several students wanted to just multiply by 2 outright or multiply the 84 by 2. Okay? It's not that you're necessarily wrong, but you're combining conversion factors. So you are making now a new, wild, crazy, foreign conversion factor. The issue with that is that your units aren't going to track out potentially as nicely, and you increase the likelihood of making a mistake. So I don't want you combining conversion factors. Keep them as independent units as long as possible. Solve it all the way out at the very end. Now,
can you go over one more time how to get the moles from the grams on the periodic table thing?
yes. Are there other questions? So just to elucidate, there's a question about where 84 came from. There are questions about anything else that's up there because I need space. Okay. To get the 84, how do we do that? We take the molar mass of sodium, which is 22.99. We take the molar mass of hydrogen, which is 1.01. We take the molar mass of carbon, which is 12.01. We take the molar mass of oxygen, which is 16.00, and multiply it by 3. We add all those up, and we should get 84.01. 23 plus 1 is 24, plus 12 is 36, 36 plus 48. I'm just going to say is 84. We just add them. Does that make sense? Does that get you, Natalie? Okay. Questions? Okay.
What's the 300, by the way, that you had down there? It's okay.
The 300 that's gone?
Yes.
Oh, that was our answer. When we multiplied everything out, we got 336. According to sig figs rules, we have to drop that to 300. So this question should look kind of familiar. I know it says quiz. Don't do quiz. Why does this question look familiar? Did I have you do it last week? I don't think I did it. How'd you do it last week?
No, we were still in Skittles last week.
I think we're still doing Skittle farts. No Skittle farts. What is this one? It's from the test. Okay? Straight off the test. Notice that there's a lot of conversion factors given in there. At this stage in the game, you know how to write an equation. You know how to balance an equation. You know how to determine the molar mass. What does this question now become on the next exam? All of that text that we had up there, all of those conversion factors disappear because you are now responsible for knowing where they come from. Here's the new question. If 9 grams of oxygen gas are reacted with excess hydrogen gas, then how many grams, of water are produced? Beginning to end, I'll give you 5 minutes, still 6 weeks out from the end of the class. This is really what chemistry is getting at. We are running a reaction and we are trying to predict something. Okay, and we're trying to predict a measured value. Okay, we are trying to make water. Why would we ever care to make water? We need water to live, so maybe it's relevant. Say if we were trapped on a Martian planet, like on Mars, and everybody had ditched us, and we were impaled with this big sharp pointy object, we need to come up with ways to... Anybody? No? Thank you. One person heard that. Yes. What's that?
How they live when they were impaled.
Watch the movie, or read the book. The Martian.
Okay.
So, what are we looking for? We are running a reaction. We are mixing oxygen with hydrogen to produce water. And I noticed everybody jumping straight out into solving a conversion, which is fine to set this up. But realize the context of what this class is. This is not a conversion class. This is a chemistry class. So probably a good thing to start with would be the chemistry. How about a chemical equation? Okay. What are we mixing? So go ahead.
Just like side question, can I do the Martian for the project thing for the block?
Well, you can talk to me after class about that. Hydrogen with oxygen to produce what? H2O. We now have a chemical equation. Is this a chemical equation that is useful to us?
No.
Why not? It's not balanced. Starting to see some, whoops. Sorry. Wrong. Stop with the booing. Okay, we now have 2 oxygens, but then we need 2 hydrogens. We now have a chemical equation. We can then go through and start to take advantage of this to help us with our conversions. Okay? So now we can jump to the conversions, which is the irritating, boring part, in my opinion. Okay? What do we want for an answer?
Grams of water.
Grams of water. What are we given?
9 grams of oxygen gas.
That is very robotic. What is our formula for oxygen gas?
O2. Where's the CERN at the end of that?
Please don't. Okay. 9 grams of O2. Ideally, I would go 2 grams of water. Can I convert substances through mass? Sorry, don't write that down. Can I convert substances through mass? No. How do I convert substances? Through moles. So I need to get 2 moles of O2. How do I find a conversion factor between grams and moles? Periodic table. So I'm just going to write as PT. What are our numbers? 32 what? 32 grams of oxygen. So the 32 shows up in front of grams. Whoops, man. And what shows up in front of moles? 1. Do we have our answer yet? No. What do we know needs to happen? I need to get rid of moles of oxygen, and ideally I would go to grams of water. Ideally. Don't write it down. Do we have that conversion factor? No. So we have to convert to something else. Okay. And this is where we run into a dilemma on what do I convert to. Remember, what we're trying to get to is grams of water. I can't go directly to grams, so maybe I should try and come up with some conversion factor that gets me closer to being water. Okay. Can I convert moles of O2 to anything related to water? Yes. That is moles of water. And this is where a lot of people stumbled. They're like, well, I don't know what to do. Well, the reason they didn't know what to do is that's what they were looking at. But if we bring the equation back, what does the equation give us? The moles of water related to the moles of oxygen. There are 2 moles of water for every 1 mole of oxygen. That factor comes from our balanced equation. Okay? Which is particularly irritating for you as a student because was the equation given to you? No, you had to discover the equation. You then had to balance the equation. You then had to use the information within that equation to come up with a conversion factor that still doesn't even solve the question because I still don't have the final answer. Now my unit is moles of water. What do I want as a final answer? I want grams of water. How can I get that conversion factor? Is there a place to find the relationship between the mass and moles for a substance? Where is that found? Our periodic table, we get 18 grams of water is 1 mole of water. Our units now come out as grams of water. We can punch it into the calculator and we'd have our answer. Yippee! Okay? No. What's the no?
It's just every time I think I understand, I don't, so I'm not going to tell you that I understand.
Okay. I can accept that. Yes, Brandon.
Why is 2 moles of H2O 1 mole of oxygen?
Where did we get the 2 moles of H2O and the 1 mole of oxygen?
Oh, yeah.
Coefficients from our balanced equation. Okay? You are pulling in information from all sorts of different sources. This is what you have to do as a chemist. Okay? This is what you have to do in any job, believe it or not. You're pulling information from different places. Okay? You're just now doing it within a chemistry context. Okay? Questions? Yippee-ki-yay. Do we really want to do another conversion? Okay. We're just doing one. I'll give you 30 seconds. Let's see what you come up with. How many molecules of sodium hydrogen carbonate are needed to make 2 molecules of sodium hydrogen? Did not read that right. Let's try that again. And that one's too easy. How many molecules of sodium hydrogen carbonate are needed to make 3 grams? I did it again. Molecules sodium carbonate are needed to make 3 grams of sodium hydrogen carbonate.
Somebody remind me to bring that back up next on Thursday.
Okay. The calculation right. Uh-oh.
Why did you put the 2 at the bottom instead of the top half? For the HCO?
Trying to convert sodium hydrogen carbonate into sodium carbonate. My sodium hydrogen carbonate grams cancel. I'd have moles of sodium hydrogen carbonate. Do I want moles of sodium hydrogen? No, sorry, I got to go all the way through it. Moles of sodium hydrogen carbonate I want as a unit to cancel. That needs to show up on the bottom. So that I'm now in moles of sodium carbonate. The 2 comes in from the balanced equation. The 2 shows up in front of sodium hydrogen carbonate. That's why I put the 2 in front of the moles of sodium hydrogen carbonate down there.
How do you know it goes on the top or the bottom?
How do I know that the moles of sodium hydrogen carbonate should show up on the bottom? I'm canceling the unit from the previous step. That's why it shows up there. It's all about canceling units. It's not top or bottom. I'm not multiplying or dividing. It's cancel a unit. Sodium hydrogen carbonate as a unit needs to disappear from the equation. It must show up on the bottom. The 2 gets tied to the sodium hydrogen carbonate. That's why it's on the bottom. Other questions? This one's fun because it brings in Avogadro's number, and since a lot of people wanted to write that down, I figured here you go. Now you have that opportunity. Okay? Questions?
When you enter that, you have to you just write 6.22 times 10 to the 22.
Yep. Okay. No. No. Water and solubility. So this is awesome. I had expected to get through all of this today, and I didn't get to it. Okay. What's going to happen when we look at water? Well, water is a bent shape, which we should remember from drawing out our Lewis structures. It will interact with other water molecules in this type of fashion. Why might it interact in this fashion as opposed to saying having a hydrogen interact like this? Why is the red one a bad interaction, but the ones shown in your textbook are good?
Was it about miscibility?
It'll get to miscibility, but not quite yet. What can you tell me about oxygen, particularly in comparison to hydrogen? Oxide versus hydrogen, sure. Why would oxygen carry a negative charge and hydrogen carry a positive charge typically?
Hydrogen only has to lose 1 electron.
Nope, not necessarily. Not a bad idea, but nope. It is electronegativity. Thank you, Sebastian. Oxygen is more electronegative than hydrogen, which means the electrons in that bond spend most of their time with oxygen. Meaning oxygen is gaining electrons from the hydrogen, making the oxygen what charge?
Negative.
Negatively charged. And the hydrogen would become what charge? Positively charged. When I look at the red interaction, I'm matching a positive hydrogen with a positive hydrogen. Is that likely to happen? Nope. I'm going to get similar charge repulsion. If we look at the interactions shown in your textbook in the dashed lines, highlighted now in blue, we're matching an oxygen up with hydrogen. What was the charge on our oxygen? Negative, and the charge on our hydrogen? Positive. That is now opposite charges. We get a stronger attractive force there. That is the force that we would predict in water because it neutralizes the charge. Okay? Is oxygen formally negative? It's a tricky question. For it to be formally negative, it would need to either show a formal negative charge. When we draw out water, do we show a formal negative charge? You should say no, thank you. Okay. Or it's an ionic bond. How do we know it's an ionic bond? Metal and a nonmetal. Is hydrogen a metal? No. So is it an ionic bond? No. So is oxygen or hydrogen formally charged? No. So when we're going through and specifying that negative and positive, this gives us an idea of how that molecule interacts because of the electronegativity disbursement. Unfortunately, if I write a negative and positive, I'm now saying it's charged, which it is not. So I need to come up with a notation that allows me to recognize that oxygen as having some negative characteristics, but is not formally negative. I need to suggest that it is partially negative, or its charge is slightly changing to be negative. What is our symbol for change? A delta. And of course, we'd think delta with a nice little triangle thing. We're using instead the lowercase delta, which looks like a weird figure 8 infinity sign as hand-drawn, but that's how we would reference it. It is the delta notation. For those of you looking at the old exams and you looked at it and were like, what the heck is this delta notation? There it is. That's your delta notation. It's recognizing that electrons in a covalent bond are unequally shared. Okay? That's what gets water its polarity or its interactions. If we're going to look at solubility now of something dissolving in water, what things are going to contribute to it dissolving in water? How can I get, say, salt to dissolve in water? What's going to happen? What does salt have? It has sodium ions and it has chloride ions. Those chloride ions are what charge? -1. The sodium ions are what charge? For those to dissolve in water, the water molecules must interact with those individual ions. Which part of the water molecule is going to interact with the chloride? The oxygen or the hydrogen? The oxygen, okay. What charge was the oxygen? Partially negative, right? What happens when I bring a negative near a negative? That repels. Is the oxygen interacting with the chloride? No. What's going to interact with the chloride? The hydrogens. Our hydrogens are partially positive charged. Those are going to interact with the chloride. What's going to interact with the sodium? Well, if it's not the hydrogen, it needs to be the oxygen. So we're seeing a balance of charges come out of this. That's one of the things that can help us contribute to solubility, is if our charges can somehow stabilize. Okay, what else is going to improve the solubility of a compound? Okay, and going from the solid to the aqueous solution, what do I have to do to all of the ionic bonds in sodium chloride? What do I have to do to all those interactions? I have to break them. How do I break forces? With energy, okay. If we compared sodium chloride on the left to now the sodium chloride on the right, what phase would you describe the left? What phase would you describe the right? There's no water there. gas. There's no interaction between them. How do we transition between a solid and a gas? How? How do you move from a solid to a liquid? You add heat. How do we increase the solubility of compounds? You add heat. Take a solid, you want it to dissolve? Add heat. Take salt water, you want the salt water to dissolve? What can you do? Add heat. Add sugar? Add heat. So if we increase the temperature, it will increase the solubility of our compounds. Okay? Before I completely let you go, I just want to introduce one thing here. We'll double back. Solutions. How do we quantify the amount of silver bromide in that equation? How do we quantify in our previous examples? What did we start with? I can go all the way back. Do we need to go all the way back? What did we quantify in those conversions that you wrote down? What did we start with? What was the mass?
There it was.
We started with our mass, a gram value. Can we start with a gram value for our silver bromide, or sorry, where our aluminum bromide came from? What's the issue with looking at the mass for aluminum bromide? If I weigh that out. When I weigh out that compound, what am I weighing? I take this species and I put it onto a balance. This is my nice little balance. No, it's not going to eat it. Here's little glass windows, right? Little box. What am I going to weigh? It's aqueous, so what am I going to weigh? I'm going to mass the aluminum bromide and the water. Is water reacting in this equation? No. Can I determine the amount of aluminum bromide through mass? No. Guess what I need? A new conversion factor. That new conversion factor is molarity. We will pick up there on Thursday and maybe move into gases. We'll see what happens.